All right, the first thing that we're going to talk about today is impedance. So impedance is the AC version of what we referred to as resistance in DC circuits. Okay. So if you recall, if we had a network that was excited by a DC source, I'm not specifying whether it is a voltage source or a current source because it literally does not matter. We defined the resistance of our network to be the ratio of the voltage drop across our network divided by the current flowing into our network. So R was simply V over I. If we take a similar network and we sinusoidally excite it, like so, if we measure the phasor voltage drop across our network and the phasor current flowing through our network, we will get what is commonly referred to as an impedance Z, defined as the ratio of phasor voltage to phasor current. So essentially this impedance Z, as I mentioned a moment ago, is just playing the role of what resistance did in our DC circuits. Okay. So because our impedance is a ratio of two complex numbers, it is going to be a complex number itself, which means we can express it in either a polar form or a rectangular form. So I would like to start with the polar form. So starting with my fundamental definition, I'm simply going to substitute in my generic definition for my phasor voltage, which is simply the magnitude of my AC signal with an angle of the angle of my AC signal. In this case, it's a voltage, so that's Vm and theta V. Down here in the denominator, I'm going to have Im angle theta I. And using the rules for dividing exponential and polar form complex numbers, we should see that this comes out to be Vm over Im with an angle of theta V minus theta I. And we can put this in the form of the magnitude of Z with an angle of theta Z. So the angle of our impedance is simply the difference between our phase angle of the voltage and phase angle of the current. And the magnitude of our impedance is simply the ratio of the magnitude of the voltage over the magnitude of the current. Impedances are given in this form on occasion, but it's more regular for us to present an impedance in rectangular form, okay? So in rectangular form, our impedance, Z, so let me just make a note here, this is polar. In rectangular form, our impedance Z is going to be expressed typically as R plus JX, okay? Where R is resistance representing the real part of our impedance, and X is reactance representing the imaginary part of our impedance, like so. So this is our rectangular, there we go, form. Okay. So what I want us to do is use those relationships that we developed at the end of our last class meeting and see if we can figure out what the impedance of a resistor, an inductor, and a capacitor look like, okay? So for a resistor, we learned the following things. So the magnitude of our voltage was equal to R times the magnitude of our current. And we learned that the phase angle of our voltage was equal to the phase angle of our current. And then we also wrapped things up with a relationship that our phasor voltage V was equal to R times our phasor current I. So we can use these three pieces of information. Realistically, we're just mainly going to work on the last one here. And what we're going to observe is that the impedance of a resistor, ZR, is most simply expressed as just the resistor value itself, okay? So the impedance of a resistor is just the resistor value. More formally, in rectangular form, this would look like R plus J0. And in polar form, this would look like R with an angle of 0 degrees. So what do you think the units of this impedance of a resistor are going to be? Ohms. Absolutely right, because it's just the resistor value itself. So all three of these expressions are indeed quantified in ohms. Okay. For an inductor, we know that the magnitude of the voltage is equal to omega L times Im. And we also learned that theta V is equal to theta I plus 90 degrees. And when we wrap things up talking about the frequency relationships for inductors, we had the relationship phasor voltage V was equal to j omega L times phasor current I. So from this relationship, we can see that our impedance, just V divided by I, is simply going to come out to be j omega L. Okay. In a more formal rectangular form, that would look like 0 plus j omega L. And in polar form, that would look like omega L with an angle, of 90 degrees. You might see some textbooks and stuff like that refer to this quantity omega L as X sub L, where that is just the reactance of the inductor, okay, representing the imaginary part of the inductor's impedance. So, two things that I want to talk about here, but let's start first with the units, okay? So, if I do a dimensional analysis of this thing, J is just the square root of -1. It doesn't have any units associated with it. Omega is an angular frequency expressed in radians per second, where radians is a dimensionless quantity, so realistically, it's not going to contribute anything either. L is an inductance measured in henries, and we learned a few weeks ago that a henry is simply a volt second per ampere. So if I put volt seconds per ampere up here, I wind up seeing that my seconds cancel each other out. Since radians is a dimensionless quantity, it goes away. And I'm left with simply volts per amp, which is another way to say ohms. So the impedance of an inductor is also measured in ohms. Okay. Now, I want you guys to notice something here, okay? For the inductor specifically, and we'll see a similar relationship for capacitors, the impedance of the inductor is dependent on the frequency of excitation for our system, okay? So let's see if this agrees with what we already know. If our angular frequency omega were 0, what would the impedance of our inductor look like? 0 ohms. What do we call something with a resistance of 0 ohms? A short circuit. What does omega equal to 0 represent? 0 AC oscillation or a DC signal. So this exactly agrees with what we already know about the behavior of an inductor, at least at very low frequencies. So at low frequencies, our inductors are going to look predominantly like short circuits. Now, what's really interesting here is that at very high frequencies, our inductors actually start to look like open circuits because the impedance gets larger and larger and larger because our impedance is proportional to our angular frequency. So this frequency dependent property of the inductor is part of why it is used in devices or circuits that are called filter circuits, okay? So effectively, at very low frequencies, if we take the voltage drop across our inductor at very, very low frequencies, it's going to look something very close to zero because our inductor looks like a short circuit. So that means it is rejecting low frequency signals. And as we get to higher frequency signals, it starts looking more and more like an open circuit, which will pass the signal through actually. Okay? So inductors, if we're taking the voltage drop across the inductor as the output of our filter, it's going to tend to behave like a high pass filter, okay? So what do you mean by flip-flop? So if we switch the position of the elements, or if we switch the capacitor for an inductor? Right. So as it starts to look like an open circuit, it will let signals pass. So it attenuates low frequency and passes high frequency. Yeah. For a capacitor, we have the relationship that the magnitude of our current is equal to omega c times the magnitude of our voltage. We have the relationship that theta I is equal to theta v plus 90 degrees. And lastly, we have the relationship that phasor current I is equal to j omega c times phasor voltage v. So from these relationships, we can determine the impedance of our capacitor will be commonly referred to as 1 over, j omega c. In a more formal rectangular form, this might look like 0 minus j divided by omega c. What I am using here is the fact that 1 over j is the same thing as negative j, and you can prove that very easily by multiplying 1 over j by a factor of j over j. Okay. In polar form, this is going to look like 1 over omega c with an angle of negative 90 degrees. And this quantity 1 over omega c is often labeled X sub c, which is just the reactance of a capacitor. Yes?
You wrote for the theta I, theta v, you wrote plus or v. Those will be minus.
It is not. Sorry, what?
So why is it still plus 90 even though
you swap the I and the V? So I have IM is equal to omega C VM. And for my inductors, I swapped I and V and replaced L with C. I guarantee I'm right. You can look back in your notes from Friday, or not Friday, Monday, unless you wrote them down wrong. But I guarantee it's theta I is equal to theta V plus 90 degrees because our current should be leading our voltage by exactly 90 degrees. And that makes that happen. So if we look at our units here, we have, sorry, that's the wrong color. 1 over omega, so that's going to look like a second per radian. And then we have 1 over C, where capacitance is measured in farads, and a farad is an amp second per volt. So I'm going to have amp seconds in my denominator and volts in my numerator. And once again, we see that seconds cancel seconds. Radians is a dimensionless quantity, so that goes away, and we're just left with volts per amp, meaning that the unit of impedance for capacitance is also the ohm. So what this actually means is that when we're looking at a circuit in the frequency domain, all of our resistors, capacitors, and inductors, we're treating them as impedances, are just going to combine exactly like resistors. We no longer have to worry about special rules for anything. As long as we're dealing strictly with impedance, it's all just a resistor as far as we are concerned. Sometimes that resistor is imaginary, but it's still really just behaving like a resistor, okay, from a mathematical standpoint. Now, if we look at the impedance of a capacitor, we can see that it is inversely proportional to frequency. So when our frequency is very low, we essentially have 1/0, which looks like infinity or an open circuit, which exactly agrees with what we learned when we first dealt with capacitors. At very high frequencies, our capacitors start to look like short circuits. So this is exhibiting a low pass filter behavior because it is passing low frequency signals and attenuating high frequency signals, okay? And you'll see a little bit more of that when you do your lab, I guess it'll be next Monday, okay, where you're investigating the effects of frequency on impedance in a circuit. So what we can do now is we can take that stuff that we learned about phasors from Monday's class, and we can take this stuff that we learned about impedance from today's class, and we can put them together to effectively transform our circuit from the time domain into the frequency domain. And the reason why we want to do that is essentially that's going to convert all of the calculus and trig that we would have to do in the time domain into algebra in the frequency domain, just using complex numbers. So essentially, if we work in the frequency domain, all of the circuit analysis techniques that we already know how to do are once again valid, okay? So let me show you what I mean by that with an example. So, and pardon my crappy memory here, but I believe in our last class meeting, we looked at the following circuit. If it's not exactly this, it was something close to it, right? So I had some current source, IS of t, connected in series with what I believe was a 5 ohm resistor, and I want to say that this was a 2 Henry inductance. Okay. And ultimately, I was concerned with finding this voltage drop, Vs of t. Okay. And if memory serves me correctly, and if I get this backwards and you happen to have your notes out, feel free to correct me, please. This current was 1 cosine, I think I did 3t plus maybe 20 degrees or something like that. Does that sound about right? 2t plus 10. Okay, we'll go back to the 2t plus 10. Our values of our components are correct though? Okay. So what I want us to do is to convert this circuit from the time domain into the frequency domain. So that means that we're going to replace our time domain current source with a frequency domain current source, or a phasor. So what would the phasor representation of that 1 cosine 2t plus 10 degrees amps be? So our phase angle is indeed 10. What's the other part of a phasor? The magnitude. So what's our magnitude here? 1. Our angular frequency is omega, is 2. So we have simply 1 angle 10 degrees amps. That's what our source is going to look like. Literally, if we're given it as a cosine, all we need to do is take the magnitude, take the phase angle, and throw the rest away. Exactly what we did on Monday, for what it's worth. Okay. Now I have my 5 ohm resistor. Well, what's the impedance of a resistor? Just the resistor value itself. So this is just going to be 5 ohms. And then here I have my inductor, right? The impedance of an inductor is just J omega L. So that's going to be J times 2 times 2 is just J 4 ohms, where we already have figured out that the impedance of an inductor is always going to be measured in ohms. So I'm going to replace this with J 4 ohms like so. And what I'm now trying to find is this phasor voltage Vs. So what I'm going to do is literally just Ohm's law. Okay. I have a 5 ohm resistor in series with a J4 ohm resistor. So I can effectively just lump these guys together and treat it as a single equivalent impedance. Yes, Carter. So using Ohm's law, we would find that Vs is simply 1 angle 10 degrees amps times 5 plus J4 ohms comes out to be 6.403 with an angle of 48.660 degrees volts, which should agree with the exact same result we got on Monday. But we did a whole hell of a lot less work to get there. So what I want for us to do, essentially for the next 25, 30 minutes or so, is literally just to work some problems, okay? We're going to work problems in the frequency domain. And as I mentioned a couple of minutes ago, that is really just going to entail us applying DC circuit analysis techniques to the circuits once we transform them into the frequency domain. So what I want to know from you guys is which DC circuit analysis techniques do you feel like you need a refresher on? So I'm talking about things like KVL, KCL, Ohm's law, source transformations, current and voltage division, superposition, that kind of thing. What is the thing that you guys have the worst grasp on, you think? Real. Current and voltage division. Okay. So I'm going to make up a circuit here. So let's say that we have the following circuit. Let's make this 1/6 of a farad. And let's say that Vs of t is 12 cosine. Sorry, that should be an inductor. That's my fault. Let's make this 12 cosine 3t plus 19 degrees volts. And let's make Is of t be equal to 2 sine 3t minus 28 degrees amps. Okay. Ultimately, what we're trying to find will be the voltage drop across our 8 ohm resistor. So I'm going to call this V8 as a function of time. And I want to find the current through my inductor. So I'm going to just call this IL as a function of time. So we are going to approach this problem, and any problem that we see like this, where we have sinusoidal signals in the time domain, our first step is always going to be to convert our circuit from the time domain into the frequency domain, okay? So that simply means that we do exactly what we did in the last example. We replace all of our sinusoidal voltage sources and current sources with phasors, okay? So what would the phasor representation of my voltage source be? 12 angle 19 degrees volts. Okay. We'll come back through and do all of our impedances and stuff like that in just a moment. Okay. What about my current source? What's that going to look like? What was that? So I do need to convert from sine to cosine. I do that by subtracting 90 degrees from the phase angle. So that's just going to look like 2 angle negative 118, right? While I'm at it, I'm going to go ahead and label the phasor quantities we are now trying to solve for. So that would be the phasor voltage V8 and the phasor current IL, like so. And now I'm going to go through and get my impedances, right? So my 8 ohm resistor is going to look like an 8 ohm resistor. My 12 ohm resistor is going to look like a 12 ohm resistor. What's my 4 Henry inductor going to look like? So J12 ohms. And my 1/6 of a farad capacitor is going to look like 1 over J omega C. So that's the same thing as negative J over 3 times 1/6. So 3 times 1/6 is 3/6 or 1/2. So I believe if my mental math is correct, this looks like a negative J 2 ohms. So I could, if I were so inclined, simplify this circuit, because I see 3 impedances connected in series. And I'm just looking for the current flowing through one of those impedances. And since they're all in series, the same current flows through everything. So I could simplify this down to the following circuit. So here's 12 angle 19 degrees volts. Here is an 8 ohm resistor. Here's 2 angle negative 118 degrees amps. And now I'm just going to put those 3 impedances in series, and I'm going to replace them with a single generic impedance. So I'm using the generic circuit element model, just a box. So what is 12 in series with J12 in series with minus J2 going to look like? 12 plus J10, exactly right. Literally just add them together. Here is my phasor voltage V8. Here is my phasor current IL. So what I'm going to do to analyze this circuit, because I want to explicitly remind you of how to employ voltage division and current division is I'm going to use superposition here. So using superposition, we're going to have one circuit where V1 is on and, or excuse me, where VS is on and our current source is off. So that would look like this guy right here. So here's my 12 angle 19, if I think that's right. This is my 8 ohm resistor for what it's worth here. Let's see. So this is going to be V8 prime. This is going to be IL prime. And I want us to solve for V8 prime using voltage division. So anybody have any thoughts on how we might do that? What's our known voltage? So 12 angle 19 degrees volts. What is the impedance we're trying to find the voltage drop over? What is the total series impedance we see? 8 ohms plus that 12 plus J10. So I'm just going to write that as 8 ohms plus 12 plus J10 ohms, exactly like this. And I'm going to throw that into my calculator. And when I do, I got 4.293 with an angle of negative 7.565 degrees volts. Yes. Is your calculator in rectangular form? My answer is in polar form, which is why my answer may be different than yours. Convert your answer to polar form. Did anyone else get my result? Okay, so I did it right. So you got to have a little bit more practice on your calculator, bud. All right, moving on. How might I solve for that current IL prime? Can't do current division, there's no current source. Sure, so we could do 12 angle 19 over that total impedance, or we could just do the voltage that we just solved for, V8 prime over 8 ohms. Either way is going to give us the exact same result because they represent the same current, right? So I could say that IL prime is 12 angle 19 degrees volts divided by that 8 ohms plus 12 plus J 10 ohms, like so. Putting that into my calculator. So I would have 12 angle 19 over 20 plus J10. And I got 0.537 with an angle of negative 7.565 degrees amps. Does it make sense that the phase angle of our voltage and the phase angle of our current are the same? Matthew, you're nodding your head. Yes, explain your nod. Exactly right. So that current IL is the same current that's flowing through that 8 ohm resistor. So we essentially have the voltage drop across the resistor and the current flowing through the resistor, and we know that resistors don't introduce any phase shift. So we would know that we made a mistake if we saw that our phase angles were different. The fact that they are the same leads us to believe that we did it correctly. Any questions on how I applied voltage division or Ohm's law here? All right, so now let's work this guy with the current source on and the voltage source off. So here's my off voltage source. Here's my 8 ohm resistor. Here's my current source. This is 2 angle negative 118 degrees amps. Here is that 12 plus J10 ohm impedance. This is our current IL double prime. This is our voltage V8 double prime. Let's start by finding IL double prime using current division. So, anybody remember how current division works? What's my known current? So 2 angle negative 118 amps. What is the impedance I'm trying to find the current through? So I'm going to do 1 over 12 plus J10 ohms. And now in my denominator, I'm just going to have the sum of the reciprocals of all of the parallel paths. So in this case, I only have 2 parallel paths. I have the 8 ohm path, so I'll have 1 over 8 ohms. And then I have the 12 plus J10 ohm path. So when I put this into my calculator, wish I'd brought my TI. I got 0.716 with an angle of negative 144.565 degrees amps. Anybody else get that result? You did not. Perhaps I typed something in wrong. Let me give it another whirl. 2 angle negative 118. 1 over 12 plus 10i. 1 over 8 plus 1 over 12 plus 10i. Back error, damn it. Nope, I got that same result. I did it 2 different ways. My calculator is in degree mode, and obviously I'm getting my answer in polar form. Still waiting for one of you guys to confirm this is right, but it's right. Several people got their hands raised, so once again, knowing how to use your calculator quickly and efficiently is probably the hardest part of all of this material. So working under the assumption that that answer is right, because it is, now how might we find that voltage V8? What was that? So we could combine the two impedances in parallel and use Ohm's law. Or we could recognize that since we know the current through the 12 plus J10 ohm impedance, and it is in parallel with the 8 ohm impedance, they're going to have the same voltage drop. Either way should work, but our current is flowing into the negative polarity terminal either way. So we could either do V8 double prime would be equal to negative IL double prime times 12 plus J10 ohms, or we could do negative 2 angle negative 118 amps, and then 8 ohms in parallel with 12 plus J10 ohms. Either way is going to give us the exact same result. Carter. So we could do KCL to find the current flowing through the 8 ohm resistor and then multiply that by 8 ohms. So that's perfectly reasonable as well. So I'll write down a third method. So that would be 2 angle negative 118 amps minus IL double prime times 8 ohms. And once again, that current is flowing into the negative polarity terminal. So I'd put a negative sign out front. So we've got 3 different ways to solve for the current. I'm going to choose one at random. You guys pick whichever one makes the most sense to you. Let's make sure we get the same number. So I just got 11.177 with an angle of 75.241 degrees. Volts. Can anybody confirm that? Mason's giving me a thumbs up. So, working under the assumption that I'm right, which again, I am, how would we proceed from here? Combine the results, exactly right. Okay, so we could say that V8 by itself is just V8 prime plus V8 double prime. So for me, because I stored stuff in my calculator, that's literally just going to be the answer I have stored as A plus the answer I have stored as C. So that would look like 12.465 with an angle of 55.259 degrees volts. And similarly, IL was just going to be IL single prime plus IL double prime, which is what I have stored in my calculator as B and D. So alpha B plus alpha D gives me 0.488 with an angle of negative 95.999. If you didn't store the values in your calculator, that's perfectly fine. You should get something similar to that, but with a little bit of rounding it. So did anybody get something similar to this when they combine the results? Okay. So I worked this problem in this particular way, specifically to give you guys a refresher on not only superposition, but also current division and voltage division. For what it's worth, there is an easier way to work this particular problem. So I would like to show that to you guys now. And this method works essentially whenever I can break my circuit down or represent my circuit in such a way that I only have one unknown quantity, okay? So if I start from that original circuit diagram in the frequency domain, here I have that voltage source of 12 angle negative 19 degrees volts. Here's an 8 ohm resistor. Here's 2 angle negative 118 degrees amps. And here's 12 plus J10 ohms. I think, let me give us the variables we're looking for. So here's V8 and here's IL. Right. I think we can solve for both of these quantities very easily if we know what the voltage drop across these two terminals is. So I'm just going to call this guy Vx, like so. And how I'm going to solve for this voltage Vx is essentially just Kirchhoff's current law. You might want to think of it like nodal analysis, but it's really just going to be a one equation, one unknown system. So more realistically, it actually is just KCL. So essentially, if I treat this bottommost node as ground, and I treat the voltage at this node as a nodal voltage Vx, I could say that Vx minus 12 angle negative 19 degrees volts divided by 8 ohms minus 2 angle negative 118 degrees amps plus Vx over 12 plus J10 ohms is equal to 0. That's literally me just applying KCL. Well, I now have a one equation, one unknown system. For what it's worth, your calculator's numerical solver cannot solve this. So heaven forbid we have to do a little bit of algebra by hand involving complex numbers to get through this thing, right? So what I'm going to do is I'm just going to isolate my Vx term on the left-hand side, and I'm going to have everything else on the right-hand side. And so that would look like Vx multiplied by a factor of 1 over 8 ohms plus 1 over 12 plus J10 ohms is going to be equal to 12 angle negative 19 degrees volts over 8 ohms plus 2 angle negative 118 degrees amps. So this term right here is just a constant that we can evaluate in our calculator. And this term over here is another constant that we can easily evaluate in our calculator. So I'm going to do that right now. I'm going to call this guy A, and I'm going to call this guy B for what it's worth. So 1 over 8 plus 1 over 12 plus 10i. I got A to be 0.1789, so let's call it 0.179, with an angle of negative 13.241 degrees. And the units of that should be per ohm. Sorry, having Let me put that back in my calculator because it's being a pain in the butt storing that value for later. There we go. And then B, now I'm putting that in my calculator, so that's just 12 angle negative 19. Oh, it should be positive 19. Thank you for that. Plus 2 angle negative 118. And when I put that into my calculator, I got B to be equal to 1.365 with an angle of negative 69.434 degrees. The units on that are amps. And so putting these two results together, I would find that the Vx that I'm interested in is literally just B divided by A, which I got to come out to be 7.626 with an angle of negative 56.193 volts. And from here, I could say that the V8 that I'm interested in is just 12 angle 19 degrees volts minus that Vx. Which comes out to be 12.465 with an angle of 55.259 degrees volts, which for what it's worth, exactly matches what we got earlier. And similarly, IL is just going to be Vx over that 12 plus J10 ohms, which I get to be 0.488 angle negative 95.999 degrees amps. Once again, exactly matching the results I got earlier. So what I'm trying to impart to you all today is that the circuit analysis that we are doing is literally nothing that we haven't already done. The only difference is that now we're dealing with complex numbers, okay? So whatever methods that you were comfortable with in the first part of the class will 100% work here. That being said, I want to make this very, very clear, and you can try to prove me wrong all damn day long. Your calculator is literally incapable of solving a system of equations using complex numbers, which means if you relied on using nodal analysis and mesh analysis for everything in the first part of this class, you are going to have a miserable experience for the remainder because it literally can't be done except on a computer. When you get your test, exam 3, which is only over effectively this material and the power relationships, I will not give you a circuit that is required to set up a system of equations, okay? It's always going to be able to be done using KCL, KVL, Ohm's law, voltage division, current division, or a source transformation to be able to use one of those other things. If you use nodal and mesh, you are SOL, okay? So you have to get a grip on the basics of circuit analysis in order to be successful for this material. You just literally can't use nodal and mesh at all and be able to do it on your exam.